Problem 34, chapter 6. In this problem, we have this half a ring, which is pinned to the ground at point O. We have this rotational spring at point O, which is rotated 90 degrees from its resting position. So currently it is applying a moment in counterclockwise direction. We know the spring constant, we know the mass, and the mass is 5 kilogram. The question is, what is the reaction force at point O? And also, what is the angular acceleration immediately after releasing this system from this condition? So we are releasing it, and we want to analyze it immediately after that. So there is no velocity here. That's something we need to know. And like the other problems, the first step is always drawing the free body diagram and choosing the coordinate that you want to use. The centroid of half a ring is going to be somewhere here. If you look at the tables at the back of your book, the distance of the centroid for half a ring from the center of the circle is 2r divided by pi. We know that from the table. So we are going to have a gravitational force here, mg. And also we are going to have reaction force at O. Depending to what system of coordinate I'm going to use, I can put those forces in the x and y direction, or if you prefer to use normal and tangential coordinate, you can actually put two forces in the tangential and normal direction. It's up to you. Both of them are fine. You can use any of these. But for this specific problem, let's go with xy coordinate. There is no really any advantage in xy coordinates, but I want to show you how it works if I use xy coordinate. We have this gravitational force. We have OX and OY, two forces here. And also, I'm going to have a torque from this spring too. And the magnitude of the torque is going to be KT times the rotated angle from the rest, which is pi divided by 2. KT is given by Newton meter per radian, so the angle must be in radian. It is 90 degrees, so pi divided by 2. This is our free body diagram, and we know this body is rotating about a fixed point, O. So the dynamical equations we can use is sum of the forces in the x direction is equal to mass times acceleration of the centroid in the x direction. Sum of the forces in the y direction is going to be equal to mass times acceleration of the centroid in the y direction. And also, sum of the moments of a centroid is going to be ig times alpha, but if you want to use that, then OX and OY they're going to show up in your equation, which is fine. But if you prefer to use some of the moments about point O, we can absolutely do that too. It makes the equation slightly simpler here. Sum of the moments about point O is going to be equal to IO times alpha. But what is IO for half a ring? There is a point over there that I need to explain. Let's do it here. If I have half a ring with the radius of r, and let's say the mass of it is m, then the mass moment of inertia at the center is going to be mass times radius squared, right? We know that from Appendix B. But how about this point? You cannot use parallel axis theorem between points between the center of the circle and this point, because the parallel axis theorem works between any point and also the centroid. We have to find it from, we need to know I about the centroid, then use I about the centroid plus mass times distance squared to find the mass moment of inertia about, for example, this point, right? And the center of the circle is not the centroid. So you cannot use parallel access theorem between here and here. But if you do that, it's going to give you a correct answer. But your solution, your method is absolutely wrong. Why this is happening, or how can I find the mass moment of inertia at this point? One way is finding the mass moment of inertia about the centroid, which the distance of it from the center of the circle is 2r divided by pi. You can use parallel access theorem between this point and this point. Then I about the centroid, Ig, is gonna be I about the center of the circle, which is mr squared. Then use, minus mass times the distance squared, mass times 2r divided by pi squared. Then after finding the mass moment of inertia here, you can use parallel access theorem to transfer the mass moment of inertia from here to here. So if I call this O, IO is gonna be IG plus this distance squared times mass, mass times OG squared. And OG squared is gonna be R squared plus 2R divided by pi squared. And if you combine them together, IO is gonna be MR squared minus M times this value is squared. It's gonna cancel out here. I'm gonna have another MR squared. So it's gonna be 2MR squared. So the mass moment of inertia at this point is 2MR squared. If you use parallel access theorem between these 2 points by mistake, which is absolutely wrong, you're gonna get the same solution. And that's gonna be only a coincidence. The other way and simpler way to find the mass moment of inertia about O is, let's say I have a full ring. Then I'm gonna have another M here, right? Then if I have a full ring, the centroid of the ring is gonna be right at the middle, right at the center of the circle. And the mass moment of inertia about here is gonna be 2m, the total mass, times r squared. And also I can use parallel access theorem between here and here. So I need to add 2m times r squared to find mass moment of inertia about O. Then the mass moment of inertia of this part and this part about point O, they are the same because of symmetry. So whatever I found by adding this half a ring, I need to divide it by 2 to find the mass moment of inertia of this half a ring about point O. So if you use that, you can simply again say O is gonna be, for half a ring, it's gonna be 1/2 of 2m r squared plus 2m times r squared. It's gonna be mr squared. 2mr squared. Same number. So this is a side note to find the mass moment of inertia about O. So let's go back to the original problem. So now we know IO is 2mr squared times alpha. And alpha, I'm going to assume it is in counterclockwise direction. You can assume the other direction, but you need to calculate the moment in that direction too, if you want to do that. So AX, AY, alpha, fx, fy, they are unknowns. I have 5 unknowns, right? I need 2 more equations. What is the other equation? Ax, ay, acceleration of the centroid, are not independent from alpha. They are related to each other, right? What is the relationship between them? You can say acceleration of the centroid is equal to, because the centroid is moving on a circle about the center, O, acceleration of it is going to have 2 components, tangential and normal. The normal component of the acceleration is 0 because there is no velocity. An is equal to v squared divided by OG, if you remember. But velocity is 0, so there is no normal acceleration. But the tangential acceleration is going to be alpha across OG. Right? So I can use alpha, which is in the k direction, cross product to OG. And so I'm going to have alpha in the k direction, cross product to OG, and if I put my coordinate here, let's say this is my X and this is Y, then OG is gonna be negative R in the J direction, positive 2R divided by pi in the X direction. And if I do the cross product, K cross J is gonna be, K cross J is gonna be negative I. We have another negative over there. So I'm gonna have R times alpha in the I direction. K cross I is J. So I'm gonna have plus 2R divided by pi times alpha J hat. And AG means AX in the I direction plus AY in the J direction, right? That's the definition of IG. This AX and AY, they are acceleration of AG in the X and Y direction. So from here, I can say AX is equal to acceleration of the centroid in the X direction is R times alpha, and acceleration of the centroid in the Y direction is 2R alpha divided by pi. So I got 2 more equations. Now I have 5 equations, 5 unknowns, right? So I can get rid of AX and AY by replacing them in terms of alpha. Then I'm done, right? So let's write all the equations again. So let me do it this way. Sum of the forces in the X direction is equal to MAX. The forces in the X direction is only OX. Is gonna be equal to mass times AX, which is R alpha. Sum of the forces in the Y direction is OY minus mg. Is gonna be mass times this value, so m times 2R alpha divided by pi. Sum of the moments about O, we are gonna have this moment from the spring, K of the spring times pi divided by 2. Moment of mg about O is going to be a negative moment, negative mg times perpendicular distance, this distance, 2r divided by pi, is going to be equal to 2m r squared times alpha. Now I have 3 equations, 3 unknowns, right? So if I call this 1, 2, 3, you can easily solve them. Then I'll let you do that part. If you combine 1, 2, and 3 and solve these 3 linear equations, you're gonna find OX is equal to 62.9 Newton. OY is equal to 89.1 Newton, and alpha is going to be equal to 83.9 radian per second square, and it is positive, it means it's in counterclockwise direction.